In this video, we're going to study how to find maximums and minimums of a multivariable function on a closed region. I have to unpack a little bit about what that even means, because in the previous video, we talked about finding local maximums and local minimums of a function, but what do I mean by the on a closed region? How does that affect the process? So just to briefly review, we've seen previously that there were several different cases for multivariable functions. You could have local minimums, so where your point was smaller than everything around it, local maximums, and then this very interesting case called a saddle point, where in one direction it looked like it was increasing, and in another direction it looked like it was decreasing, and those we called saddle points. And in our previous video, we had a very nice method to determine where these local maximums and minimums were. The first step was basically find the critical points for the function. That was where the partial with respect to x and the partial with respect to y was equal to 0. This is very analogous to the first step back from single variable calculus, where you took the derivative set it equal to 0. Now we're taking the partial derivative set it equal to 0. And then the second step was that we used the second derivative test to classify them. And the second derivative test was a little bit convoluted, but you took a lot of second partials like fxx and fxy, and this second derivative test gave you the information as whether it was a max, a min, a saddle, or whether it was inconclusive. Okay, so that was the method before and was great for finding local maxes and local minimums when there was no other restrictions. But now I want to imagine that I impose the restriction that we are in some closed bounded domain. For example, imagine I wanted to figure out the maximum and minimums of some function, 2x squared plus y squared minus y. But it has the condition that x squared plus y squared has to be less than or equal to 1. Okay, so how do I visualize this? Well, the first thing I want to talk about is the parabola, the 2x squared plus y squared minus y. I can plot this, and indeed it's just a parabola. Now, if this was all we knew, if we wanted to find local maximums or local minimums, well, we do the previous method. And indeed, it's clearly as a parabola, it's got one minimum at the bottom. And we could use the previous method to figure out the exact location of that minimum. Indeed, we'll do that in a moment. But now I want to focus on the other part, the x squared plus y squared less than or equal to 1. The less than or equal to 1 means it's not just the boundary circle x squared plus y squared equals 1, it's that and all points inside of it. So what this really looks like here is this cylinder. So I've drawn in my sort of light blue the intersection between the cylinder and the parabola. So now I think I understand my problem. I'm trying to find the maximums or the minimums of that blue parabola. Given the constraint that I am only allowed to consider points which are inside this cylinder, x squared plus y squared less than or equal to 1. Okay, so visually, what do I think my answers are? Well, the minimum still seems to be that minimum that we saw before. It's the smallest possible value of this parabola. And indeed, it visually appears that it is inside of that cylinder, and so it's allowed. But what about the maximum? Now, if I didn't have the restriction about the cylinder, there would be no maximum, because the parabola just gets bigger and bigger and bigger forever. But if I demand that I'm inside of x squared plus y squared less equal to 1, it means that the possibilities for the maximum have to lie on that particular curve. And in fact, there's two of them. One is right up here, and it may not be obvious from the image, but in fact, the other peak has exactly the same height. So there's actually two spots where a global maximum is going to occur. So the way I think about this is the highest value of the parabola that is still inside this cylinder. Now, there's a couple other points that I'm just going to label as interesting. One is this one that we have down here. It's the smallest value along the boundary curve, that intersection between the parabola and the cylinder. Now, this is not a local minimum. You can go lower down on the parabola to that global minimum, for example. So it doesn't actually qualify as a maximum or the minimum, but it's still an interesting point, and I can imagine that it might fall out of our analysis. Likewise, it might be a little bit hard to see, but if I just sort of rotate this for a little bit, along the backside, I have another interesting point. It's kind of like a local minimum along the boundary. Now, it isn't actually a local minimum because I'm allowed to go inside the cylinder, and that means I can have points right beside it that are smaller than it. But nevertheless, this point is also interesting and may also fall out in our analysis. Okay, so graphically, I think we have a picture of what's going on here, but how do we solve this algebraically? Perhaps the first thing we should do is just quickly run through the computation to find that global minimum that was really on the interior of our cylinder. So if we apply the previous method of first finding the critical point, so okay, the partial derivative with respect to x is just, well, 4x here. Setting that equal to 0 gives x equal to 0. Partial derivative with respect to y is going to be 2y minus 1 Setting that equal to 0 is going to give the value of y equal to 1/2. So there's only one critical point here. Our critical point is 0, 1/2. And if I want to know what is the function value above 0, 1/2, well, I can just plug it into the 2x squared plus y squared minus y, and that's going to give me that the function value of that point is negative 1/4. So negative 1/4 is my claim to be that local minimum value. Graphically, I haven't talked about that boundary cylinder at all right now, so I just have the parabola, and we've seen this point here. Now I'll just label it as 0, 1/2. It's a little hard to tell from my graphic, but indeed that minimum does occur directly on top of the y-axis when x is equal to 0. Now, I've called it a local minimum value, but perhaps a little bit prematurely because I had seen the graphic and I know it's a local minimum. I mean, how do I actually know for sure that it's a local minimum if I didn't have my graphic? Well, I have to go and apply step 2. So, okay, let's just take the first step done. We found our critical point. Step 2 then is to classify that critical point and decide whether it actually is a minimum or not. To do this, as we've seen, we have to use the second derivative test, which is a lot of analysis of the second partial derivatives. So I have to figure out fxx. If I do that computation, it's equal to 4, which is a positive number. So that's good. I'm hoping I'm on my second bullet point here, which reads that f has a local minimum if fxx is going to be greater than 0, but that's only true if in addition we have that condition that the fxx, fyy minus fxy squared is going to be greater than 0. So to test that as well, so I'll just plug that in. If you plug in those partial derivatives, you get the value of 8, which is greater than 0. So yes, the second bullet point is satisfied, and indeed, as we already knew, this is indeed a minimum. Okay, that's great, but I haven't added anything new to this video from the previous video. Now let's do the portion along the boundary. The other option for maximums and minimums, besides critical points, are boundary points, points that live along the boundary. Indeed, you can see this even with just a simple, indeed, you can see this even in just first-year calculus. If you just take a simple parabola, for instance, if you have a fixed domain, a fixed region, then those boundary points could also be maximums. So you always have to test the boundary as well as the critical points. It's just that in a multivariable case, the boundary is actually an entire circle. Okay, so we have to get that circle in there somewhere. So, I mean, our function is 2x squared plus y squared minus y, as we've seen. But how do I reflect the notion of the boundary? There's actually a couple ways to do this. And the first way I'm going to do it is try to parameterize the boundary. And a circle has a very natural parameterization using the angle theta. I can say x is cos theta and y is sine theta along the boundary. Depending on what your boundary curve is, you may want to use some other parameterization, but it's really nice if you can express it in terms of one parameter. I'll show you why in a moment. Okay, now that I have this, let me just go and get my f of theta. So I just written the entire function now just entirely in terms of theta. This cleans up as 1 plus cos squared theta minus sine theta. Now, the reason why this is good is that I've written it as a single variable, theta. And so I can compute f prime of theta. That is, I can do the kind of optimizations we saw in single variable calculus where you take the derivative and set it equal to 0. By using this parameterization, my multivariable function along the boundary has turned into a single variable function of the parameter theta. Taking this derivative, I get this expression, minus 2 cos theta sine theta minus cos theta. I'll factor the cosine thetas out the front of this just to clean it up a little bit. And now I have my derivative that I want to take this and I want to set this equal to 0. So what this is going to tell me is the theta values where the function along the boundary is maximum or minimum. And together with my previous critical point, those will give me all the candidates as to where my function is a maximum or a minimum. Well, okay, setting this equal to 0 is the product, so there's two different components to it. Cosine of 0, this is going to be 0 when you have theta equal to pi over 2 or 3 pi over 2. The second factor, the minus 2 sine of theta minus 1, if that is equal to 0, this is just the same thing as saying sine is equal to negative 1/2. Okay, how do I solve this? Well, you may recall there's the special triangle, the 1, 2, root 3 triangle, that is angle pi over 6. So in this case, sine of pi over 6 is 1/2. The only difference is that it's sine of theta equal to minus 1/2, not plus 1/2. So to help me figure that out, just as a very quick review of our trigonometry, I usually like to put up the graph of sine, and I'm trying to think, it has the value of minus 1/2, which by the special triangle we know has to do with sort of increments of pi over 6, but I have to figure out which increment of pi over 6. But the two locations where it's minus 1/2 are 1 pi over 6 beyond pi and 1 pi over 6 beneath the value of 2 pi, so 7 pi over 6 and 11 pi over 6. Nevertheless, we have just these two different values, and so solving the second factor here is theta is 7 pi over 6, 11 pi over 6. So what I have is 1, 2, 3, 4 values of theta, where along that boundary, which is now parameterized by theta, at those 4 values of theta, we have interesting points. Critical points of the single variable function f of theta, if you like to think about it that way. And so I just need to figure out, well, which of these is biggest, which of these is smallest, and I'm just going to make a table. So, I mean, it would take a little bit of time to plug this in, but I've got the 4 different theta values. I know that x is cos theta and y is sine theta, so I just say, okay, what is x and y for those theta values? I plug those in. And then I can ask, well, what's the height? What is the f of theta? So I take my f of theta, plug those values in, and I get these numbers, 0, 2, 9/4, and 9/4. So that is all of my sort of interesting points along the boundary. Okay, so let's compare the table with our graphical picture here. I've recolor-coded everything so it identifies with what we've seen in the past. Now, I have 4 different points along the boundary here, and perhaps I'll say, well, the biggest of them is the 9/4, and there's 2 of them. These occur at the theta values of 7 pi over 6 and 11 pi over 6, or if you prefer, you can convert them to the x and y coordinates. Regardless, we have these 2 different spots where you have this maximum value of 9/4. Okay, what about the pink ones? Well, those are the ones that I'm going to label as interesting. The one that's going to be a height of 0 is at the bottom. It's that sort of the dip that you have in the boundary curve. And then the 2 was that point around the backside, in between the 9/4, a little bit smaller than the 9/4, because 2 would be like 8/4. And then these 4 points that I've analyzed all came from analyzing the boundary. The final thing I'll add was the point we analyzed earlier, which was that global minimum, which was at the beginning, and that had the height of negative 1/4. So now we have an answer. The absolute or the global maximum of this function in this domain, well, the maximum is the 9/4, and the absolute minimum is the negative 1/4. And then the other 2 points, the 0 and the 2, they may well be local minimums to the function constrained to the boundary curve, but to the function that's inside of, so allowing the boundary or inside this particular cylinder, they're actually nothing at all. They're not local minimums or maximums or anything. They're just points that sort of fell out in our computation. I said there was a couple different ways to do this. I'm just going to very briefly talk about the second way you could do it. So I'm going to go all the way back to step 3 of the computation. This was where previously I had introduced the parameterization. I introduced theta. The other approach you could do to get that boundary curve into the function is just to directly substitute it. So perhaps I will rewrite it as x squared is 1 minus y squared. So I can say my function looks like 2 times 1 minus y squared plus y squared minus y. In this case, this is now entirely in terms of y, and it actually works the same way. You could then take the derivative with respect to y, set that equal to 0, solve for the y's, solve back for the values of x. You'd actually get all the same points, and I'd encourage you to pause and try to do it that way. Now, which method you use, sort of directly substituting it in or finding parameterization? Well, it sort of depends on the actual question that's being given. When you directly substitute, like this new method I'm telling you about, well, often you don't actually cleanly manage to rewrite it as a function of just x or a function of just y. You need it to be a function of just x or just y if you want to use the single variable method of taking a derivative set equal to 0. On the other hand, the useful parameterization also depends on the shape of the curve. When we've got a circle, doing cos theta and sine theta is very natural, but of course, depending on what the curve is, there might not be a nice natural parameterization. Okay, so to sort of summarize what we've learned, we're actually using a theorem, and it's called the extremum value theorem. We saw the extremum value theorem back in Calculus 1, but we see it here in multivariable calculus once again. If you have a multivariable function, so f is going from Rn to R, and that function is continuous on a domain that is closed and bounded. So the closed means that it's including that boundary, so less than or equal to 1 versus just less than 1. And the bounded means that the domain is on some sort of finite region. It's not sort of exploding to infinity. If both of those things are the case, then f does attain a global maximum and a global minimum. And that's really what we've used when we were doing this particular problem. In fact, we really actually saw that there were 2 different cases. The minimums or maximums could be in the interior of the region. That's when you do the idea of finding the critical points in the second derivative test. Or it could be that the maximums and the minimums live on the boundary of the region. And that's what we just did in this video, where we parameterized or find some other way to substitute that boundary curve into the original function. And so we always have these two steps, sort of check the interior and check the boundary.